Okay. Hi everyone. Welcome to the tutorials of statistical mechanics. I'm going to teach you the course. I am Joseph Aces. This is my email. You can write me anytime I'll answer you. And you can find me here in this building in room 213. Anytime you can write me an email if you need anything, any time, any question about the homework, about the course, and we can meet on my office. And the first thing that I want to talk to you about is a brief review of Maxwell relations, right? Okay, so we have the thermodynamical potentials, for example, the energy, right? Free energy, which is let me right, and as you saw today in the lecture, we know that the internal energy is actually an exact differential, an homogeneous function, and thus it is an exact differential. So we can see this as du d. Here, this is the entropy, the temperature, the pressure, volume, chemical potential, and number of particles, right? Okay, and you saw today the Durkheim-Gibbs relation, right? That it's this equation. Right? Okay. And the idea of Maxwell relations is that take the advantage of knowing that the energy is actually an exact differential. So we can write this, yes. And since since this is an exact differential, that means that we can equate the cross relations. So, for example, we can do the derivative of the temperature with respect to the volume. And this should be equal. And this should be equal to making the derivative of the entropy of the pressure with respect to the entropy, right? dP. And such we can construct the Maxwell relations, right? Any questions now? Okay, so these are in general how we construct the Maxwell relations, and we of course know that since this is an exact form, like exact derivative, we know that, for example, t is the derivative of u with respect to s, right? At constant volume and constant number of particles. Okay. Okay, so this was just a little summary of what Maxwell relations are. But today the tutorial is going to be about thermodynamical equilibrium. Who can tell me what does it mean, thermodynamical equilibrium? What do we understand by thermodynamical equilibrium?
Entropy is maximum. Entropy is maximum.
Okay.
And energy is constant.
Entropy is maximum.
And energy is constant, no?
Not constant. Minimum. But Stas today told you something different, a little bit like what is the consequence of thermodynamical equilibrium? If this is true, then what happened to the intensive variables?
Also minimum?
No. Suppose we have a system, right? A, B, and C.
They're all equal to each other.
Exactly. TA, TB, TC, then TA, TB. This also happens with the chemical potential, with all the generalized forces, right? The chemical potential, the pressure, and you can put here torsion, like whatever you want, whatever generalized function you can think of. But there is a condition. We need to allow the exact differentials to move. Think like if you have a system, two systems, right? Let me make here a little picture. This is A and this is B. And here we have pressure 1 and pressure 2. And we want them to be at equilibrium. But here we have a rigid wall that cannot move. This system cannot reach equilibrium with the pressure because this barrier forces each system to retain its own pressure, right? Otherwise, if you allow this barrier to move, let's say that this can go left or right, then the pressure can nivellate itself. Like the pressure from system A and pressure from system B can reach some sort of agreement in which both they are get to the same point. Okay. So this is only true if this is very, very important because it's like if the pressure, like all the intensive variables are the ones that dictate how the system moves, but the things that actually move are the open variables, the entropy, the number of particles. That's the change on the actual change on the system. So if those variables are in some way constrained, the system cannot change. Okay? This is like a very important concept. Okay, so let's illustrate this with an example. suppose we have a system like just the same that I drew before, A and B, that have a free energy. Okay, so we start with a system that has these properties. At the beginning, this wall is rigid and do not allow any heat transfer or anything. These are two isolated systems from each other and from the outside. Okay. So So if this is the case, can we say that at equilibrium B1 and B2 are equal? Perfect. Okay, let me put here this example. Okay, then assume we remove this constraint. We put, instead of this wall, we allow something that allows heat transfer. Then we are asked to answer 3 questions. A is the energy at equilibrium. B is how, like, when we say that the system 2, the system B, let's say, transfers heat and C is that we have to prove that this relation holds between the pressure and the number of particles and the volume. Well, okay, that's the task. We have this system, and we are asked to solve this question. Okay. How would you start with the first question?
What is the question?
it's
What's the energy?
what's the energy of the system after reaching equilibrium.
Write down the energy of each,
Like, the energy,
each side.
let's say, sorry?
What do we do is write down the energy for each side first.
Right, exactly. We have, like, we want to find energy 1 and energy 2 at equilibrium. So let's start writing the energies at the beginning. A and B. This I is for initial, the beginning. Okay. So what would be the total energy of the system here at the beginning?
Both of them, the sum of them.
Exactly. We know that energy is an additive quantity, right? Okay. And what do we know, like which of the conditions that we know that must hold at equilibrium we can actually use in this system?
Temperature.
Exactly. So we say that TA must equal TV, right? What do we know about temperature? What is temperature in general? With respect to energy?
dE to ds, or the opposite.
It's, let's see, we know that E, dE is T ds, right? So it is dE
d
to ds. Sorry, this is partial derivatives. At constant volume and number of particles, which we know that this is true because we have these two conditions, right? So they are not allowed to change. Okay? Sorry, I forgot to tell you that here the entropy, let me put it here, big, is given by this function. Okay? So we just perform the derivatives. Sorry, sometimes instead of, like, I use E and U interchangeably. Okay? Sorry for that if it gets you confused. So let me change here to E. Here I am just making the derivatives. Okay, so why didn't you tell me it's the other way around, right? It's ds right?
But
But you just
wrote the
explain.
opposite. You wrote dE equals T times ds.
Ah. Okay, true. No, but 1 second. Okay. Okay, so we have that since T A equals TV, we can just invert, right? It's the same thing. Right? Do you agree? Right, the only thing that I did here is just to derivate the u, right? And there's only this alpha there. These two must be equal. So this a and this a cancel. This alpha and this alpha cancel. And we have that u alpha minus 1 of a, b of a to the beta, and n a gamma. Right? Any question? Okay. So then we can just say that UA over UB alpha to the minus 1 is just B dB theta. This would be just ND the gamma, right? Any question?
NB is 2 and L.
Sorry?
NB is 2 and L.
Right. So we can just put here a 2, right? Yes. Okay, so we can just put this. We can put just the energy of the system A as a function of the energy of the system B, right? And this is 1 over.
Oh, what are they?
Right? So we have this expression and we have this expression, right? And then we have two equations with two variables which we can solve, right? You want me to do the algebra or it's okay if I just do the answer?
Okay.
Okay, then u1 would be 3 times u2, u2, u1, this is beta squared. Okay, so this is the answer to the first question. It is actually very easy if you say like this thing, you set this to some sort of variable, I don't know, x, and it's very straightforward to see that this is the answer, right? Okay, so let's go with number 2. Any questions of did we solve? Of how we use the equilibrium condition? We just use the fact that the energy is additive, it's a very important property, and that at equilibrium all the intensive variables must be equate if their conjugate variable is allowed to vary. Okay? So this would be B. Okay? Well. Okay? B is just we need to find a condition to know when B is the one that transfers heat to A. How do we put that in a mathematical statement? Right? This must be that Q2 must be less than 0, right? Why?
Because it's the one.
It's the one that it's conceding the energy. Okay, so this is kind of straightforward. We can say that the energy of the system 2 is just the change in the energy, is minus the change of the energy in system 1, right? And from the first law of thermodynamics, we know that the heat transfer of any system is equal to the change of the energy plus the work, right?
What is U2 equal to negative delta U1?
It's the amount of change in the energy. I'm just naming. I'm just naming the energy. Like I'm just saying that the energy that it gains. So I can put it like this, right? Okay. What's the amount of work that this system makes, that system 2 makes? Let's put here 2.
No work.
Why?
No distance. No
Right.
change
In volume. Right? dV is 0. Perfect. So, like using this, you can see that dQ2, you just have to plug these numbers into here. It's equal to 1 minus 2 E2 V1 So, what's the answer of the exercise? Like
If this equation is negative.
we need exactly. We need this to be bigger than 1, right? Okay?
Could we have said it's it moved from B to A if the temperature in B is higher than the temperature in A?
Okay, you're asking if we know that. And actually, the thing is that that's true because why can we know that that's true? Because it's the only variable that can change, right? That can contribute to the statement. But it's not only that; it should be accompanied with the relation with these variables, with volume and the number of particles, because you can have a little small system, right, with a very few number of particles, and it then actually crosses the system. But that's true. If only if only temperature is allowed to vary, then the system with bigger temperature is always the one that it's conceding the heat to the other system. Right? That's what we saw in thermodynamics. Okay. So yes, if T D is bigger than Ti. Okay. Okay, for C, we also need to assume that we can exchange particles. Okay. So they ask us if we allow the exchange of particles, we need to show that this relation holds. You cannot see it, right? Let me plug it in. Okay. So then we write then the change of the energy as du TdS minus TdV plus mu dn, right? And we are now interested in this quantity, right? So if we have constant energy and constant volume, right, we have that the chemical potential is given by minus T ds to the n, right? Agree? Okay. So how do we enforce equilibrium in the chemical potential, like in this equation? We just equate both, right? So this means, and since we are at equilibrium, okay, so dA, ds, d mu, dn, constant u, constant v. How can we enforce another equilibrium condition here in this equation? We can say just the temperatures are equal, right? Just the same. So then we're left with the variation of the entropy, which gives us, this is the same dot. Right? And we actually know, what can we say about pressure? Again, from the fact that it's a total derivative, like the entropy is also total derivative, we know that V1, it's pressure 1, right? You can see it from here. If we don't allow the energy or the number of particles to change, we have this relation for the pressure. So then we have P1, P2, How much time do I have left?
2 minutes.
2 minutes?
Yeah.
Okay. Okay, we have these two relations. Okay, this, I don't know if you can see that. So there are a bunch of cancellations happening here. Like these two ways cancel, and we can actually get to the relation that P1 over P2 equals V2 over V1 times N1 over N2. And this is the answer to the third one. Okay? Like this is a bunch of algebra just using these two equations. Okay? Like you can substitute for, like, take some of these equations, substitute it in here, and get that the only variables that are left are these B1 and B2. And for example, this n cancels to the gamma minus 1, cancels with this n to the gamma, so it's left only one. Okay? Okay. Can you hold for 5 minutes, or do you need to go?
Okay.
It's okay? Okay, so there is also another exercise I want to discuss, which is the usage of a thing called compressibility. This is this k tau. This is minus 1 over v. I think in your homework you need to show that this is true, right?
Mm-hmm.
This must hold, right?
No, that wasn't part of the homework.
No? Okay, so you can actually use Maxwell relations to prove that this is true using the fact that the entropy is always increasingly monotonically with respect to the energy. Right? Like, I don't know how to put it. It's like this. Right? Okay, so the idea is that using this relation, you can actually prove that Cx, this is, you can put here, it's the heat capacity at constant pressure or volume. You can put anything here. So you just, this is defined as dq on dt on x constant. Okay? And you can show this because you get that Cv is T to the ds on dt at constant volume, right? From the expression of the energy. I think I erased it, but you get this. And you can also show that Cp has exactly the same relation, just at constant pressure. and you can actually use, okay, so ds constant volume, just yes. You can then just show that the entropy this is just the chain rule, right? The S must depend on P and T. It can depend directly in T, or it can depend on T by means of P, right? This is like in mechanics you did something like this a lot of times. And then you can write that the heat capacity at constant pressure can be expressed as ds to dt constant volume and ds to dp this you can use Maxwell relations to show that this is actually, sorry, okay, and like similar, and then you can use these relations that we got for the heat capacity at constant volume to show that this must hold. Cp minus Cv is equal to d dv and you know the triple, like the triple relation. I think you had to prove it also in the homework, something like this. But this is from actually calculus, in multivariable calculus.
אנחנו עדיין
יש עוד 9 דקות כאילו
תן לנו עוד דקות, 2 דקות.
2 דקות?
תודה. So this is a relation from multivariable calculus that if you take the cyclic derivative, you get -1, right? And we now use the definition of the heat of the compressibility, that it must hold to be bigger than 0. And then we get that minus B times KT must be equal to D, P, D, and dB. Sorry, it's a bunch of derivatives. A little bit hard to follow, but the expression is that we get from this relation and using the definition of compressibility, that Cp minus Cv it's T over BKT.
יש פה הרצאה עכשיו.
דקה, סליחה. Okay, so this is bigger than 0 for sure, and we know that this is also bigger than 0, right? From here. So this means that CP is always bigger than CD. Okay.
It's because of the work, right? Because in constant volume the work is 0 and then all the energy goes to the heat.
Exactly.
Okay, thank you very
Okay.
much.
Of course. And please reach me out to the if you have any questions.
And teleconnect.
Sorry for the run at the end.
זה גם יעזור